Okay, welcome to your ENGG1500 Week 3 lecture on engineering problem solvings, or at least the method that we use to solve not just engineering problems like your ENGG1500 problem, but also all sorts of other things. That's a really cool method. I use it all the time, and I'm going to show you a bunch of examples of how it's been useful to me. So hopefully you'll learn something awesome today, maybe blow your mind a little bit. It's going to be great. Before we launch into that, I'm going to smash through a little bit of housekeeping stuff pretty quickly, and then we can get stuck into it. So, video descriptions. This video description is going to be pretty enormous by the time in the next 24 to 48 hours when I fill it all out. And there's a reason for this. What I'm going for is, I know there's a lot of communication of all sorts of different information coming through 1500 in all different ways. What I'm going to try to do is everything from me. You watch the lecture. If I need you to do something else, go to the video description. There'll be a link to it or something like that, okay? So you get an assessment this week that I'm going to talk about in a second. There's a link to that in the video description. It's also going to be up on Blackboard and all sorts of other places. But if it's content that comes from me, super simple thing to do, watch the lecture, everything will come out of that, all right? And also if you open the video description, it's massively long and there's all sorts of jazz in there, there's a reason for that. I'm trying to streamline the way in which I give you information. I did mention assessments, so your first quiz, it will close on Monday, so if it's not done by 5 p.m. Monday, that's it. You don't have another option, so make sure you get in and you smash that out. It's got a couple questions in there like, have you read your project description and stuff? If you understand your project, but we haven't put a project description up yet or something like that, just say yes. Get 21 out of 21, okay? Your other assessment, Assessment 2, your first report, officially comes out on Monday, and I'm going to issue it today, and there'll be a link to it in the video description below, okay? So don't stress about it now. It's a report, but in order for you to do that, you need to have consumed this lecture, so consume this lecture first, and then go and watch that. Awesome. We had a sick live stream on Tuesday last week. It was really good, really engaged group, super fun. I had a great time doing it. And something that we tested in the live stream was rehashing some new examples related to lecture content and doing them live. Seemed to go down an absolute treat. So I've prepped some examples for us to do in the live stream on Tuesday. So it'll be kind of complementary content to this. Not repeated, but better. It does rely on you having seen the lecture first, though. So watch the lecture before Tuesday, 8 a.m., and then we'll smash it out in live stream and have a great time again. Just to clear some things up, just to be sure for everybody, your official way of receiving information from me is lectures and Blackboard. Discord is a thing that I hope you find useful, but if it's just spamming you constantly, you can mute some of the channels, like the memes channel and stuff like that. Just mute them if you don't want to buy into that part of Discord. You so don't have to, okay? I'm hoping it's more useful to you, not a distraction. So if it's good, great, use it. If it's not, mute it. If you're keeping track of everything on Blackboard and everything in the lectures, you will not miss anything by not engaging heavily in the Discord. On the other hand, if you want to engage in Discord, obviously I'm on there pretty much all the time, so you can get access to me. Some of you met Strict Dylan this week, and occasionally you will notice that I have two sides of my personality. One that's happy-go-lucky, and one that's you need to get it done, and you need to get it done now, okay? And that's part of being a professional, all right? So there are some bits of being at university where you will be held accountable to things like being on time to class, working in a team, doing things in timely manners. And if you don't do it, you got to meet Strict Dylan. If you did, don't worry about it. This was a thing. It wasn't great. It has now been sorted. We're back to happy Dylan, okay? Don't feel that just because you made a mistake in week 1 of university, I'm going to hold you to it for the rest of your life. It's totally all good. Okay, the last little thing to cover before we launch into the real content. This lecture has a whole bunch of different examples. I try to pull examples from different fields to make it a little bit more relatable to people, but don't assume the example is going to have anything to do with your field. It's on you to some extent to sort of look at these weird and wacky examples and try and extract the useful information from them, because we can't do 10 examples for every different project. The other thing is I'm going to jump between examples really quickly to make specific points every now and then. You don't need to fully understand the example, just understand the point I'm trying to make and then try and extract that and apply it to your projects. But it can be a little bit of information overload if you try to follow every single example. But we do have one main example that we're going to use throughout the whole lecture here, the next 2 or so hours. And that's what I'm going to present to you now. So, engineering problem solving. Let's look at our example. The Sydney to Melbourne airway is the second busiest in the world. So depending on when you look at the data, in 2008 it was the third busiest airway in the world. Sydney to Melbourne, just there. In 2019, it actually became second, and I don't know where it is now because of COVID. But super busy airway, and Sydney, Brisbane's pretty busy as well. This is worldwide, so Australia coming out of Sydney has got 2 of the busiest airways in the entire world, which leads to crowded airports, huge logistical issues because you've got planes taking off pretty much constantly. If there's a tiny delay, it wrecks everything. That's a problem. We need to expand, and Australia is only expanding in terms of the amount of air travel it is doing. Well, again, it was. So, what's the solution to this? You've got a really busy airport. What do? Well, you build a second airport. This is the solution. This is the Western Sydney Airport. This is the design, and this is where they're up to in construction at the moment. And that will solve the problem, we assume. We're going to go through today how you figure out whether this is actually a good solution to the problem, or what you should do when you get given an engineering problem. How do you go through all the possible solutions and settle on a design? And how do you make sure that the design you settle on is the best? And that's the kind of the kicker that we're going to look at today. So, this is a presentation of the engineering method with all the steps in it: problem identification, research, scoping, research, potential solutions. That's what we're going to cover today. And then you kind of get into the nitty-gritty side of it: detail, construction. So you build the thing, you deliver it to your client, and then you evaluate it. This is what you're essentially going to do through the second half of the year. So we're going to cover the top half of this today. I'm going to give a bit of a disclaimer here. If you look this up, you will find 100 different variations on the engineering method. You will find it called different things. And I do think it's a misnomer to call it the engineering method, because you can use this to solve all sorts of problems. They don't have to be engineering problems. And I use a particular set of words. I actually have, this is my own particular set of lists. Most people omit research, for example. Don't worry. It can be called different things. It super doesn't matter. All right? What matters is the concepts that we're going to go through, not what you call them. The process is intended to be descriptive, not prescriptive. What I mean by that is it's supposed to help you solve a problem, not tell you exactly how you have to do it at every step. It's supposed to be informative. It's not supposed to be dictatorial. It's a framework, not a straitjacket. So just to give you some examples, I've used this process in the middle of COVID last year. We converted ES126 into a room to make masks and respirators. Not masks, definitely not masks, sorry, face shields and respirators for COVID scenarios. So that was one type of problem that I addressed with this. I've also used it to make demonstration rigs for my thermal storage materials. This is what we spoke about in the live stream, and what we might speak about again on Tuesday in the live stream again in a little bit more detail. And I actually used this process last year when I had to take my entirely practical ENGG1500 course and put it online. So as you can see, these are 3 drastically different types of problem, and we're going to look at a totally different type of problem again today. We use the same method, but we use it in different ways every time. We adapt and we evolve. We don't get locked into one specific way of thinking. That's going to make this so much more useful to you if you can acknowledge that. So it's a little bit different each time, but having the structure really helps. So, a couple of years ago, I did a bit of startup training before we spun our company out, and they spent months teaching us how to do customer discovery and analyze problems, not like an engineer, but like an agile startup. And it's the same thing. It literally is the same thing. It just has a different focus and it uses different words, but the structure is pretty much identical. So, just interesting. Awesome. All right, number 1, and this is the most important thing that we are going to cover, and I think we're probably going to spend the most amount of time on it, and it's problem identification. You've got to absolutely nail this, and I'm going to take you through how. Let's do a weird random example to start. Let's assume I'm a hotel manager. I have a 10-story building and it's got one elevator. My guests keep leaving negative reviews about my hotel, saying the elevator wait is too long. I come to you and your little engineering team and say, solve this for me. And good little bunch of engineers that you are, go and make my elevator faster. You install a new lift, you increase how quickly they move, and improve the algorithm means once you've got more than one elevator, who do you send to pick up people on different floors? Totally valid. And it is a very solution-focused way of thinking about the problem. Elevators are slow, make them faster. But problem identification. If we look at our real problem, they're not leaving negative reviews necessarily because the elevators are slow. They're leaving them because waiting is annoying. Human beings have problems like not elevators being slow, but I don't like to wait for things. It's totally valid. But once you can acknowledge this, there's a whole new set of solutions. We don't have to necessarily speed the elevators up. We can make the waiting process less boring. And we can do that in really cheap, really effective ways. And so it's a totally different way of solving the problem that may be much cheaper or much more effective or much better in some way because you did a better job of identifying what the core problem was. Okay? And the hotel manager, their problem is negative reviews. If their negative reviews go away because you installed some mirrors and a hand sanitizing station, they're going to love you. If you charge them $200,000 to install a new lift, they are not going to hire you again. Also, sorry about that slide, like cutting my face off. It wasn't the best slide I've ever created. So the point of my story is identify the actual problem. So an overcrowded airport, similar problem, all right? We got to be careful. Are we treating the disease or the symptom? The crowded airport is the symptom. It's not necessarily the fundamental problem. It's not necessarily the disease. It's the symptom. So let's take a step back. Why are our airports crowded? Well, it's an air traffic route between Sydney and Melbourne, which has a lot of people that are in one of those places and want to be in the other one. All right? It's a problem of moving people around. It is not a problem of airports. It's a problem of moving people. And there are other ways of dealing with this. All right? So when we can take that step back and go, there are people in Sydney who want to be in Melbourne or vice versa. All right, we're not limited to an airport-based solution anymore. And you will find this happens almost all the time. Very rarely do people have well-defined engineering problems. They generally have a human problem. I don't like waiting in line. What can you do about that? They very rarely have a problem that prescribes a particular type of solution. So identifying our problem, crucially important. So this is another kind of counterexample. Does building new roads decrease traffic? And most people would think, yes, if we put a new road in, it's going to decrease congestion. There's going to be more space for the cars to go, and we will have less traffic jams, and everything will be better. And it turns out that is so not what happens. When you put new roads in, you actually get just as much traffic as you had before. What happens is more people now go, oh, driving is a good way to get to my destination, so more people start to drive. And traffic generally rebuilds very quickly to roughly the same level. So to reduce traffic, you don't do it by putting in more roads. You do it by putting in more public transport, because that makes driving a less attractive solution when you can get public transport that's super efficient, okay? So this is why problem identification is key. If you identify this problem as if you identify traffic as we don't have enough roads, putting in new roads will never solve it. You will piss money away to never get the outcome you want. Good problem identification says, okay, let's upgrade the rail network. Let's change something else to make it more beneficial to not drive. Cool. So some reasons why. Yeah, okay, so it's all about understanding what problem you're actually trying to solve. So let's smash through a few other cool examples where we get to see this. Really common problem at the moment in my world is I have solar panels. Somebody has solar panels on their roof. They only work during the day. They don't work at night. They want to get power out of them at night. What do? Really obvious solution is you put in some batteries, right? And you get some Tesla Powerwalls or whatever your favorite type of battery is. You bang them in your garage, and now you've got power at night. Kinda. Yeah, you're not wrong. But if we take a step back and go, what was the real problem here? Well, why did we want to put solar panels on the roof? Well, in general, that's because we want to reduce the amount of CO2 we produce. Because climate change is bad. So if we acknowledge that's our real problem, our solution space blows open. If we acknowledge that's our problem, well, we could go nuclear instead. If we went nuclear, we'd have 24-hour power, no CO2 emissions. Perfectly great solution to problem. In fact, an absolutely brilliant solution to problem in countries like France are running 95% nuclear power really, really successfully. We could diversify the sources of renewables that we got our power from if you wanted to stick with renewables. So wind is generally strongest in mornings and evenings, right when solar panels are starting to work pretty poorly. So diversifying where you're getting your sources of renewables from is a super good way to solve this problem. You could solve the problem still with sunlight, but by doing it in a different way. So instead of going PV panels, you could go fields of mirrors, or actually you can even do this with PV panels as well. And instead of storing the energy in an electrical battery, you store it as heat. And it's way cheaper to store energy as heat than it is to store it in like batteries as electricity. And then you have a power cycle that turns it back into electricity when you want it. Great solution that I may be slightly involved in. This is what my company does. So, but it's a totally effective way of solving this problem. You could look at it even more broadly. Go carbon capture. Burn as much coal as you want. Don't care. We're going to suck it back out of the atmosphere, and we're going to sequester it. That's the word I was looking for. I don't know how well you can see, but that thing down there, that's a ute. That's like a Hilux ute. These things are enormous, and they're constantly sucking air through, sequestering carbon out of it, and thus reducing the amount of CO2 in the atmosphere. So that's one way of sequestering carbon from the atmosphere. There is another. It's slightly simpler. Go and plant some trees. That also works. Growing plants sequester carbon from the atmosphere. There is an idea that you could go and pour some fertilizer into the ocean and deliberately start enormous algae blooms, which take huge amounts of carbon out of the atmosphere when they bloom, and then they die and they sink to the bottom of the ocean, and you could sequester billions of tons of carbon that way. You could do it. The other option is big interconnected grid. So this thing's really cool. They are going to build an enormous PV station in Australia and run a power line all the way to Singapore. And because it might be sunny in Australia when it's dark in Singapore, as you connect up bigger and bigger bits of the grid, it's sunny somewhere on Earth. As long as you can connect that to everybody else, you can solve the problem that way. So once we acknowledge that there is our real problem is something to do with not wanting to put more CO2 in the atmosphere but still provide people with power, we realize we can solve it in thousands of different ways. And some of these are way better in certain applications than electrical batteries. To give you some context, there is more thermal storage installed in the world already than every electric battery ever made by humankind. Yeah, because it scales super well. So just ways of solving the problem well beyond what you probably first think your solution space may look like. Point is, there's more than one way to do this. And engineers tend to be solution focused. We tend to get given a problem and go, I have a way to solve that. And then you pick your solution and you just brute force the hell out of it until you get it to be something pretty good. And because you're an incredibly intelligent person, you can do that. You could pick any one of these options and you are smart enough to figure out a way in which you can make it work. But if you can step back and acknowledge that the solution space is bigger than that, you can probably find a better or easier solution to brute force. Okay? When you go into startup world, this is called customer discovery, and you talk about your pains and your gains of your customer. So instead of coming up with a new gadget to sell somebody, what you do first is you go and call literally often call hundreds and hundreds of potential users and ask them about their day and what was good about it and what's bad. And then you can hope, or their work or their whatever space you're trying to fill. And then you design a thing to fill the void that causes them pain throughout the day. Pain being, I don't like waiting or whatever. So that's just, it's the same thing. That's just what they call it in startup space. You'll often notice that design briefs you were given start in the wrong place. A lot of design briefs will start with, this is what we want our solution to look like, go and engineer it. And if that's the design brief you're getting, yeah, just brute force a solution to it. You're probably not going to get somebody to listen to you that there's a better way to do it. But design briefs will often start in the wrong place. A good design brief shouldn't prescribe a solution, it should describe a capability. And we're going to touch on that again. But it shouldn't be, this is the thing that I want you to make. It should be, this is the problem that you need to solve. I don't need you to speed up my elevators. I need a way of making my customers happier in this scenario. One of which may be speed up elevators, but there may be more. So, understanding the core of the problem is really important. Being able to take those few steps back, see the forest for the trees. What are we looking at? You will notice that you see this periodically through, sometimes it's Kickstarters and things like that, but it's also just products that you'll see get put out that they might be engineering marvels from a technical perspective, but they're not solving problems that human beings actually had, and so they just flounder and die. Okay? It happens all the time. So, cool. In relation to this, in relation to the whole, you get given a problem, you see a solution, and you know you can brute force it. This creates first choice fixation. Creates the fact that once you get an idea in your head, you are locked into either thinking that's a good idea and you compare everything to it, or thinking it's a bad idea and you still compare everything to it, and you're just as locked in. So first choice fixation is really bad. And the worst thing you can do is take a problem that you don't understand particularly well, settle on an idea, and push it forward in spite of everything. Which is why I keep telling you, don't start trying to solve your problems yet. You don't know enough about them. Wait. Wait until you've seen this. Wait until you've done 4 or 5 weeks of workshop content. And then in week 5, we will start looking at this. So, yeah, don't get an idea in your head on how to do it. So once you're down the rabbit hole, you get what's called a switching cost. To swap from that idea to a new idea becomes really hard. The further you go down, the more difficult it is. This is also sometimes referred to as a sunk cost fallacy. Just because, don't cling to a mistake just because you spent a long time making it. And you'll see this all the time. People go, but I've been working on this for days, weeks, months. Look at all of the detail that I've done. Yeah, man, you're solving the wrong problem. This is a bad idea. Oh, but I've worked all of these things out. I've created all of this. Look, my model is way more advanced than yours. Yeah, cool. Still never gonna be a great solution to the problem. And you need to be able to go, yep, I was wrong. Put it in the bin. Start again. And the amount of times that it will save you to just put it in the bin, take a blank piece of paper, start again. Okay? If you've gotten stuck on a bit of first choice fixation, if you've already started trying to solve your problems, take any of that work you've done, put it away, don't pull it out again. If your first solution was the best solution, through this method we're going to show you, you're going to arrive at it anyway, so you don't need to start with it. And that's what I'm saying. The method that we're going to go through today is, that we've already started going through, is the way in which you hopefully arrive at the best solution. And it may be the one you started with, and that's totally fine. It's just how we know that we're right. Awesome. Okay, so how many steps back to take? So problem identification is generally a great way to do it, is to just play the 2-year-old toddler and ask why. But why? Oh, we need to build a second airport. But why? Our airport is crowded. But why? Because lots of people want to fly between Sydney and Melbourne. But why? Well, they want to see their family. But why? Eventually so keep asking why, and you'll be able to get those steps back and realize, oh, a lot of people want to move between Sydney and Melbourne there may be other solutions other than airport. That's great. That's super useful to you. They want to see their families. Maybe useful to you. You might be able to do something with that. But beyond that, why do they like hanging out with their families? I don't know. Maybe you can make them not want to hang out with their families anymore, and maybe that's a valid way to solve your problem. But it's probably beyond something you have power to affect. Okay? So eventually asking why stops being useful. And once you go, yeah, that's great, I couldn't do anything useful with this information, then you've taken enough steps back and you can stop. Yeah, if you can't affect change with that information isn't useful to you. Just like what we did with models and assumptions, right? We talked about making more complex models until the point where that wasn't useful to you for you to do anymore. Do you need to compensate for relativity in the distance between Sydney and Melbourne? No. Yeah, you could do it. You could go more advanced, but it's not helping you, so don't bother. Same deal here. Okay. Yeah, we covered all of that. Yes, they may want to see their families, but you may not be able to make them stop wanting to see their families. So, okay, so this is kind of a slightly different way of looking at it. Combustion of fossil fuels is not sustainable. Cool. There's a certain amount of things that you can do within your own home to help that, but you don't control your country's GDP, right? You don't get to shut down hospitals and stuff and say, no, we're spending that taxpayer dollar on renewables rather than caring for people with COVID or whatever. Country has a limited amount of resources. If it wants to spend them on going renewable, it has to take them from somewhere. But you don't have control over that. You can't change. I mean, obviously you can vote with your wallet and stuff like that, but there's only so much that you can realistically do as a one individual. And there's no point trying to solve it in a way that you don't have power to affect. Cool. So this is problem identification. It's super important that we understand that we're solving the right problem. We look at our problem, we ask, why is it a problem? We try to understand the human beings involved in it and what they need in order to have a successful solution. None of this says that your first idea is the wrong idea. It may be perfectly right, but we're just there to make sure that what we are solving is the correct problem. When you do this correctly, you should be getting more solutions to your problem, not less. Okay? So if you're doing problem identification and what it's causing you to do is restrict your way of thinking or your ways of solving it, you're probably doing it a little bit wrong. You probably should be getting more and more options. This is a divergent thinking process. What are more ways we could solve the problem? Just in case, you don't want to listen to me, there's plenty of people on the internet who agree with me, and if there's people on the internet who agree with me, I must be right. It's just some funny ways of saying it, or some, I think, fairly profound ways of saying it. And it is really, really important. If you define the problem correctly, then you almost have the solution. Steve Jobs. Yeah. I think that this is something that I'm certainly not the first person to come up with this process. And you can look around and you'll find many, many other people who are saying basically the same thing. Cool. Just sort of, there's a couple of slides before we finish up this section. I want to take you down just a 2-second rabbit hole. When I did this as startup training and we talked about doing customer discovery and calling your customers and saying, hey, what are your problems? Validate market solution fit. Do you think that this is a good idea? Or I'm going to make the thing that my customers told me they wanted. This is in a lot of ways super useful because it means you don't make a product that nobody wants. But on the other hand, customers don't always know what they want. Both I may have a few problems with the man Henry Ford. He did definitely change the world in that he created the first very popular sets of cars, and people went from riding horses to driving cars in the matter of one generation. And when he spoke about it, he said, if I had asked the people what they would have wanted, they would have said faster horses. In general, lay people don't understand problems well enough in order for them to dictate the way in which you solve them. You can get information out of them, which can be super useful, but it shouldn't dictate your decision-making process. You're the engineer. You're the one who needs to analyze that and figure out the better solution to the problem. The other, more temporary example of this is when Apple went and removed their headphone jack or their physical home button or any of the other things that they ripped out that all the Samsung lovers in the world laughed and laughed and laughed. And I was one of them. I laughed when all my iPhone friends lost their headphone jack, and my brand new Samsung does not have a headphone jack. Yep. If you did customer discovery says don't take the headphone jack out. But the innovative engineers knew better, so that's what they did. So it's a little bit tricky to know when to draw this line, and you will learn how to do it with experience, but it's just something that where different ways of viewing this will give you different outcomes here. Awesome. So this whole talking about what your customer wants, and a good way to think about this problem is to do this human-centered design. I'm not saying it's perfect, but it is a really interesting way to look at problems. So this is what your discipline-specific videos are going to be on next week that I'm going to make over the next 24 to 48 hours. What you do here is you take the problem and you essentially put a human being at the center of it. So we don't need to make an airport. We need to meet somebody. Let's meet Dylan. He needs to get to Melbourne from Sydney. Hi, Dylan. Why do you want to go to Melbourne? I want to watch a cricket game at the MCG. Cool. Now we've got a human being here, and you can begin to empathize with me, and you can begin to ask me questions, or at least put yourself in my shoes and try and think this through. As you do this, you can go, all right, what are parameters that this person might think is important, and what are parameters that they might not? And it should get you to start realizing that there's aspects of your problem that maybe you haven't thought through particularly well yet. And that's basically where you get your video on, and if you can do a little bit of that, it should make your actual hard numbers engineering solutions better. Cool. Yep, I'm pretty sure that's everything I wanted to say there. Oh, yes, it's definitely everything I wanted to say there. That is essentially problem identification in a nutshell. It's really important, okay? If you can't identify the correct problem, doesn't matter how technically brilliant your solution is, it's not going to get adopted, okay? Because nobody's going to want to use it. So we do problem identification first. We make sure we get it right, because it'll set us up and everything will be easier from this point. So after problem identification, which is not easy to do, but let's say that we've done it, we go on to scoping. Now, scoping and problem identification are not necessarily mutually exclusive. Scoping is basically around taking your identified problem and setting some bounds or putting some numbers to it. So it's defining our solution space. What are we actually talking about? The nice one-liner example is it tells you how big your problem is. To give you a bit of an example, we've been talking Sydney to Melbourne, right? And we're thinking of solutions that are potentially useful to us here. And we're thinking about things like planes and stuff like that. But if you wanted to move people between, let's say, Sydney and Newcastle, what does your solution space look like? Well, it becomes more plausible to drive or to ride or freaking walk, I don't know. If we want to move them to Melbourne, well, there's a different set of solutions. You could still drive. You probably can't walk anymore. You might want to fly. If we said Sydney to Switzerland, we get a different set of solutions again, right? And now it doesn't necessarily mean that different ones aren't valid in multiple scenarios, but having this kind of image in your head of this is roughly how big our problem is helps you to define what solutions you should be going for. So here are the things that are supposed to be in a scope. Who your user is. Who is the person you're designing this for? Because you may not be designing this for everybody. In our case, commuters versus tourists might be two different users, and they might have different sets of requirements, and you might be designing your solution might be different depending on who that particular person is. How big is it? And we might mean physically how large is the object, how far is the distance, something like that. But it might mean other things like what capacity, how many people do we need to move, how much is it supposed to cost? Is that per trip, or is that total, or is that infrastructure costs? How long does it take? How long does it take to get to Melbourne, but also how long do I have to build my solution? What requirements do you have? What would you need in order to do these types of things? What are our desired outcomes, and anything else that's critical to performance. So this is not a comprehensive list. This is just probably a basic list of stuff that I would expect to see in every scope. And you should be able to apply this to your ENGG1500 projects, right? Put a size on it. All of them have some size limitation generally on what they're capable of being. And that might be a size or a capacity physically, but it might also be software-wise or programming-wise, or how much of a database do you have, or what microprocessor are you using, or what program do you need to write in. All of that can fit into a scope, right? How long do you have? Like, you've got 12 weeks in order to develop this, and then your solution needs to run for some particular period of time, for test day or whatever. So you can do all of this for your ENGG1500 project. It's generally, when you're trying to do a scope, super advisable to collaborate with either your client, if somebody's giving you a problem and saying, solve this for me, collaborate with them as you write your scope, and or collaborate with your end users. If you're trying to make something and sell it to people, you've got to be talking to those people going, what do you think of this? Is this a limit that we want to obey or not? Okay, so don't do a scope in isolation. We've given you a scope. We've given you a project description. It implies a scope. You will need to do some scoping work yourselves, and you will need to discuss with your client regularly through your ENGG1500 weekly meetings and workshops and stuff what some of the other limits in your scope are. Having a really good scope is something that we're going to circle back to in about, 30 or 40 minutes in this video, and it's going to be super useful. Now, you may not have a brilliant scope the first time you write it through, and that's okay. You can iterate out a better scope, but the better your scope is, the easier another part of this process is going to become. So spending some decent amount of time in getting this nailed is super useful. Okay, this is going back to an example. This is our Sydney to Melbourne thing. I've done a little bit of scoping here. I found a document that sort of scopes the project. It's 146 pages long. So we're not going to go through all of that. We're going to have a look at some bits of this and put some numbers to it. So you can actually find that the Western Sydney Airport is designed for commuters and tourists. That is clearly who their user is. They state that. Some other things that I found out is point to point, 706 kilometers, or if you want to take the road, 855 k's. The airport has a maximum size of 1,800 hectares. That's what they've been allocated. Currently, they move about 9 million people a year, 25-ish thousand a day, and that is expected to double in the lifetime of the airport. So it's going to need to be able to take 10 million people itself per day, per year. Sorry. 50 to 100 flights a day. So that's every couple of minutes you've got to have a plane taking off, right? We've got some budget constraints. We know the usage costs at this stage. This was pre-pandemic numbers, so obviously some flight prices have moved around. But if you're selling tickets for substantially more than a couple $100, driving there or taking the train starts to become a more plausible option. So this may dictate what your solutions look like. These are some of the costs involved in different ways of solving it. There's also a capital investment cost set at 5.3 billion, so you can't spend more than that. We have some timelines as well. They're a super useful thing to put in. We get some timelines on how long it would take to get between Sydney and Melbourne in different ways. And we know in our case of the airport, it has a completion date. It had a 10-year design and build cycle. It started in 2016, needs to be finished by 2026. Some requirements for this project, you would need the land. And if it's that big, that would be a government thing to issue the land to build something like this. If you wanted to build a railway, you would have a similar problem, or a road, you would have a similar problem. You'd need to get land from the government, and there are probably some permits that go with that. Like, this is now going to be considered airspace that you can fly in. And you would obviously need to get a sum of money, like $5.3 billion of it. There's a very clear outcome that this airport is designed to meet. So that's always a good thing to have in your scope. What is your overall goal? What is the outcome of this thing going to look like? And your client would need to agree to that before they would fund you. And you might have other success criteria. So these ones are a little bit harder to define because they're much harder to put a number on, but that doesn't mean they're less important. So what are the environmental impacts, the social or the political impacts of this particular body of work? A lot of things nowadays, if you talk about climate, for example, there are big environmental, political, social impacts of those things. There's also risk. So different solutions will often have a different level of risk associated with them. So some people are doing design and solutions which are very stock standard, off the shelf. They're not going to be particularly innovative. There's not going to be anything particularly new in them. They are generally considered low risk solutions. They're also probably not going to be substantially better than anything that's already on the market. Then there are other people who are going, I'm rolling the dice here. I have an idea. This could be brilliant. It could be absolutely terrible. That would be a higher risk investment. You might make a lot more money. You might end up absolutely losing everything. And often you'll see big companies going for more off-the-shelf, low-risk solutions, and you'll see startups rolling the dice on higher risk, higher payoff things. And all of this is stuff that can be included within your scope. As long as your client agrees to it, you should be good to go. Okay, so some of our other objectives here is we're really only trying to apply bounds at this stage. We're not trying to prescribe a solution in a scope, we're just trying to bound it. So this would be move at least 10 million people a year. You can move more. More is great, but you need to move at least 10. It can't cost more than $5.3 billion. If it costs less, that's brilliant, but it can't cost more. They're lines in the sand. You can come up with a brilliant idea, but it can only move 5 million people a year. I don't want to hear it. So that's what our scoping stages are for. Really interesting, a really well-written scope is the scope for the F-35. So the new advanced fighter plane, when they wrote the scope for that originally years ago, it doesn't specify plane anywhere. Did not have to be a plane. They specified a capability. It needed to push a battle line forward and do all of these military things that it needed to do, communicate with fifth-gen fighters and enhance the capabilities of other aerial assets and this type of stuff. None of that says plane. It just says these are the capabilities that we need. And people made planes that could do that, but that was never a requirement. That's a good scope. It puts bounds on something and it doesn't prescribe a solution. But that's really hard to do. Your ENGG1500 projects are not as prescriptive as you may have first thought when you first saw them, and it's one of the reasons I try not to give detailed project briefs early because it locks people into one way of thinking, but you'll notice that even if I call something the wind turbine project, nowhere in the brief does it say that you need to build a wind turbine. You can build anything you want, okay, as long as it solves the problem, and we worked very hard on writing open scopes to allow you to do that. And you will work with your client. So your scopes are not complete. Your project briefs are not complete scopes. You will need to work with your client throughout the rest of the semester to get a complete scope. Okay. It's still often quite difficult for students to understand why you need a scope and why is it so important. And often when you are a self-contained team, it's not that important to have a scope. When it's really important to have a scope is when you're collaborating with other people and you're trying to figure out whose responsibility it is to do certain things that were maybe unexpected. So there is a whole subreddit of Not My Job. That's not where I stole these from, but apparently there is a whole subreddit. Not my job. I had a scope of work and it was to paint lines on the road, not to move trees out of the way. I don't care. Not my job. I was employed to pave the road, not to take the pole out. Not my job. Wasn't in my scope of work. Somebody hits that and dies, don't care, wasn't in my scope of work. It's not necessarily the attitude that I think that you should have, but this is one example of where scopes become super important. When you need to interface with somebody else's technology, which is like 99% of projects. Very, very few projects exist in a bubble. Almost always you will interface with something else. And where lines get drawn is super important. If we have a look at, just going to flick back super quickly. Okay, let's look at our airport, for example. Cost $5.3 billion operational by 2026. That was written pre-COVID, obviously. COVID happens, pretty much everything gets shut down for a huge period of time. Most construction has correspondingly been delayed. One of these two things is probably no longer plausible to do. Either it's been delayed by 12 months because of COVID, or if we want to still get it done by that date, we're going to need more money to employ people on double time or whatever to get it done. Who foots the bill for that? Because if you signed off, yes, I will build you an airport by this date with this, and then the pandemic happens, government goes, hey, not my problem. You signed the piece of paper that said I would do this thing. So where that line gets drawn in a scoping document can be incredibly important and incredibly costly, which is, there's a term called scope creep, and this is what I was scoped to do. Oh, we realized the problem was slightly different to the one that we originally thought it was. Can you do this extra little bit instead? Or this thing that we thought would be easy is actually really hard and it's blown out to be this bigger thing. This is called scope creep, and most large companies hate it with a passion because it's really hard to budget for and it can cost you money. And so they will set unbelievably rigid scopes and will not accept any creep. Whilst this can be good for a lot of reasons, it can also make them incredibly hard to deal with. If you don't have a perfectly well-defined problem, it's impossible to deal with somebody who can't deal with scope creep in some way. The term agile business is something that they use around startups all the time. Oh, these people are really good because they're really agile. Essentially what that means is they don't really care if something is in or outside of scope. Their job is to help solve this problem and they'll do it however they can. That's an agile business. Once it gets to the point where it has got these really rigorous things set in stone of this is how we do things, we don't do it any other way, and that wasn't in scope, so I'm not touching it, that's when you are no longer agile. You're no longer adaptable. You've got all this inertia that you have to go through. So scoping documents can be changed, and they're changed all the time, but it's how many runs through the lawyer's system and how many months does that take before you can change something can determine how agile or how rigid you are. So both are valid in different circumstances. It's just a thing. Awesome. So our scope defines our problem. Puts a box around it of what will be and won't be a usable thing to our problem. It puts numbers to our problem identification is essentially what it does. Now, this is going to be a shorter section because it's a section that is normally omitted from the engineering method. You will rarely see anybody do this. They will say, just write a scope up. How do you not know how to do that? I don't know how to do that. I've never seen this problem before. You walked into ENGG1500 2 weeks ago. You'd never seen anything to do with the problems that I'm showing you here. You got to learn something about them. And that's what you're doing right now. In your workshops every week, you're learning a bunch of content that's going to help you solve the problem. You can't solve a problem you don't know anything about, okay? You can't write a scope. You can't even do problem identification to a problem you know nothing about. So often you'll get a problem, go, cool, I don't understand that very well. I'm going to go and do a whole bunch of research on it. I'm going to learn a lot about it, and then once I know a lot about it, I'll do some more problem identification, maybe some more research, maybe some more problem identification. Then I'll try and get a scope, and then I'll do some more research, and then I'll try and start. So this can take an enormous amount of time. It's that whole customer discovery that I was talking about earlier is also research. I would call that research. And it's generally omitted. It's just assumed that you already know everything about the problem you're about to be given, and you can tell me exactly how long it takes and exactly what steps are in it, which I think is in general total trash, especially for young engineers. Yeah. So looking at, say, for example, our models and our assumptions. Do we understand the models that are being used? Do we understand the conventional assumptions here, or do we need to go and research into these and figure out, oh, we actually need to go and do all of this extra maths and science to understand this particular thing, to make a model, to make a solution that's accurate enough to solve your problem. I chuck it in here as step 3. As I said, it kind of belongs earlier than that, and it kind of belongs later than that, so it continues throughout the whole process, but at some stage it's worth sitting down and going, cool, I'm just going to learn a whole bunch about this stuff. And some of the things you should be trying to learn is, has problems like this one already been solved before? Because most of them have. As I said, a lot of the time as an engineer, you work with other people's solutions and you integrate them. If there's other things out there that already solve part of the problem, you might be able to buy them off the shelf, integrate with them, solve the problem. So have people solved this or similar problems before in the past? If they haven't, why have they not? Also, there is supposed to be a thing that was meant to appear there that I'm assuming is going to appear in a second. But if this hasn't been solved before, why not? Is this literally the first person to ever think of a problem like this? Or is it a problem that somebody's tried before, failed for some particular reason, and you want to not make that same mistake? Cool. If they have solved it already, what is it called? So knowing the name of the thing is half the battle. And once you know what it's called, you can do research around it. Is it tractable? So if the reason that they haven't solved the problem because it is either impossible or simply impractical with the resources that are available. Can this thing even be solved? Or the answer might be yes, but the solution is so absurdly expensive or slow or difficult or whatever that nobody wants to adopt it. Knowing this before you make the same mistakes as somebody else, super useful. Cool. This probably should have been a blue slide. There may be a blue slide coming after this. But these are the first 3 steps. Then we're going to get into potential solutions. So we've identified our problem. We kind of jumped the gun a little bit when we did the whole renewable energy thing and I threw up all these different potential solutions. We're going to do that next, okay? We're going to do it with our airport problem, and I'm going to take you through this process. This is pretty involved. We're going to smash it out hopefully pretty quickly, but it can be a big process. You're going to get to do this in week 5. So we're setting aside part of your week 5 workshop for you to go through this process. So don't do it yet. Wait until then. But I want you to see how to do it. Hey, there's the blue slide. Awesome. So we know what our problem is. It's bounded. It's solvable. We understand the research behind it. Now we can start trying to solve. All right. So how do we do this? We're going to go through what we call a divergent and then a convergent thinking process. So I'm going to deliberately get you to try to go broad, and then we're going to narrow down. Then we're going to take that, and we're going to go broad again and narrow down. And hopefully each time we start going super broad, and then we narrow down to plausible. And we'll go fairly broad, and then we'll narrow down. And we can take our pretty good solutions, go broad in different ways of solving them, narrow down again. All right, so we're going to go back and forth between these 2 different ways of thinking. And the more you do this, the easier it is to switch between the 2. And you can actually get your brain to engage 2 different places at once and do these things simultaneously, although that's super hard, but we're going to start trying to get there, okay? So you'll see this drawn up in all sorts of different ways. I'm using my words here, divergent thinking and stuff. You'll see it written as different things like ideate and create and stuff like that. Awesome. This is a way of doing creative problem solving. So it's super hard for somebody to walk in and go, solve this problem creatively. Do it now. That's not generally a really great way to do this. But if you have a structure like this, it will allow you to basically go, oh man, I'm not feeling it today. That's okay. Start following this structure. You'll warm up, you'll get involved, and it'll become really good. Okay? I'm yet to fail to get a room to become creative doing this, but I can do that successfully because I have a very specific structure that I follow. Yes, structured creative thinking is an oxymoron. I get it. The irony is not lost on me. I do find I've done this, with hundreds and hundreds of people for many, many years, throwing people in a room and say, go brainstorm a solution is in general a total waste of time, which is why I don't let you do it until after you've had this lecture. In this environment, attitude is super important. So you may have noticed I've had a slight attitude adjustment. You need to be upbeat. You need to be positive. You need to be engaged if you want this to work. Otherwise, it is a total waste of time. Don't bother if you don't want to be upbeat, positive, and engaged here. Okay. Being negative about this just tanks the whole process for everybody involved really quickly. So we're going to try and smash this out. It's going to be super good. As I said, I've done this. It works better when I can do this in front of a room of 700 people, I know, but it's going to be awesome anyway. It does work better in a team. It is heaps easier to do with, I find about 10 people is kind of the ideal, but I've done it with 700 in a room and I've done it with one other person. Doesn't matter. Cool. We covered all this. All right. So this is my way that I like to do this the most. I like to go. Let's take our problem, and we're going to do move people between Sydney and Melbourne. And I'll go, give me a way to solve this. And what we're going to look at is embodiments and approaches. So if you give me a very detailed way to do it, I would call that an embodiment. And if that happens, I'll try to back it out to like a more general approach. And then we get our more general approach, we can go, hey, there's actually 4 or 5 different embodiments of that. Or that embodiment has 3 or 4 different approaches. And we can bounce back and forwards each way and spray more and more ideas out. Okay? Yep. So approaches are conceptual ways of doing it. Embodiments are the more detailed version. Engineers tend to come up with embodiments easier than approaches. That's fine. Give me an embodiment, then turn it into an approach, then turn it into a bunch of embodiments. If you get a cool approach, turn it into embodiments. Yep. You want to be creative. There's no wrong. This is the whole. There's no wrong answers. Give me something. Give me anything. I will turn it into something useful. Okay. So no time to be negative here. Smash this stuff out. Once you get some weird ideas on the board, and get 4 or 5 or 10 or 50 weird ideas on the board, turn your engineering brain on. Go, all right, this is the problem that I have. This is a way. How can I make this work? Give me something stupid. Give me, we need to stop a speeding car that no driver, I don't know, something like that. We could cast entangling roots and use vines to slow the car down. All right, turn that into something useful for me. That's what median strips are. They plant trees on median strips on like M1 motorways and stuff like that. So when a car veers off the road, it gets slowed down by the trees. It's super effective, super practically used way of turning a ridiculous solution into something awesome, okay? So chuck your ridiculous solutions up. We're going to turn them into something awesome. We can generally use them to strengthen our good ideas. So this is best, I believe, done on a whiteboard, and I've tried to take my whiteboard and do it to you through a set of slides. This is not the best way to do it, but we will deal with what we can in an online lecture environment. So let's move some people between Sydney and Melbourne. We can do it in a plane. Cool. I assume you knew that. But let's take plane and let's go for a couple more detailed embodiments of this solution. We could go in like an individual one-person plane type Cessna deal, or we could go in something like an A320, the kind of common planes that you see fly there, the Airbus A320s. Cool. 2 solutions. Awesome. Let's do something creative with it. Airbus. Airbus like bus, right? Like actual bus. We could bus people between Sydney and Melbourne. Perfectly valid solution. Bus. Let's go back again. Turn that into an even higher level approach for me. To bus somebody is to drive them along the ground, right? Terrestrial transport. All right, give me 5 different ways of moving people from Sydney to Melbourne along the ground. We could drive, we could walk, we could ride a bike, we could ride a horse, we could ride a motorbike, we could take a train, there's heaps and heaps of different solutions here, right? Sweet, we've got like 20 things already, and this has taken us all of 60 seconds. But eventually you're going to start to run out of steam. You followed this rabbit hole down and you're running out of a bit of steam. All right. What do? Let's pick an avenue we haven't gone down yet. Plane. Let's go back the other way from plane. Instead of an embodiment, go to a concept. We did terrestrial transport. Let's do aerial transport. Let's move people through the air. Give me a way to move somebody through the air that is not in a plane. There's loads. Take them on a helicopter. Launch them on a trebuchet. Great, we got a bunch of options. Now, we got a ridiculous option, right? We got trebuchet. Stupid thing, put it on the board anyway. Now, engage your engineering brain for me. Turn this into something useful. Trebuchet. Launch people through the air with a trebuchet. How is this different to the other forms of air travel that we have? Well, the other forms of air travel that we have so far are all powered the entire way. A trebuchet isn't. That's something that you put a heap of initial energy into it early, and then you let it just sort of glide to the solution. And maybe from this you get glider, which is awesome. But there's another thing here, which is that's how space travel actually works. You put a huge amount of energy in at the start, get them up to some enormous initial velocity, and then they just glide from that point onwards, because there's no drag, there's nothing to slow them down. We could launch them. We could put them in a rocket, and we could launch people between Sydney and Melbourne. And I put this concept together 5 years ago, and at the time, this guy hadn't even landed a booster rocket yet. But this is not so ridiculous anymore, is it? He landed his Huge big thing like 2 days ago. So we got spaceflight, all right? Now, this is not exhaustive, and you could just keep doing this over and over and over again. And people will say, give me 100 ideas. And you'll be like, what? How do I get 100 ideas? Well, that took like 2 minutes, and we got like 50. So it's not that hard for a team of people to get 100 ideas. Some are ridiculous. Some are useful. Some ridiculous ones we can turn into useful ones. Let's look at spaceflight, all right? So maybe to you, spaceflight is still a bit of a pipe dream. So I want to ground this a little bit for you. Sydney to Melbourne is just over 700 kilometers away. I don't know why I wrote greater than. It's approximately 700 Ks as the crow flies, right? Do you know how far away the edge of space is? If you went straight up where the edge of space is, there it's called the Kármán line, and it's 100 kilometers up. That's it. It's 100 Ks. And anywhere above about 70 something Ks, the air is so unbelievably thin that if you had enough velocity to fly, you'd have an orbital velocity anyway, which is how they originally defined the Kármán line. Not the point. The point is it's only 100 Ks. It's not that far. It's closer to space than it is to Sydney. Hell, it's closer to space than it is to Gosford, I think. In 1944, the Germans had V2 rockets that they would launch from mainland Europe to bomb London or England or whatever they were doing. They flew 88 kilometers up, and they essentially flew through space. And if they went straight up, instead of trying to go up and out, they had a 206 kilometer ceiling. In 1944, they were moving 1,000 kilo payloads, 320 Ks, half the distance to Melbourne, and they were doing it by going through space. This is not an absurd notion. This was a reality. And it was a reality 60 or 70 years ago. Okay, it is most certainly a reality now. And yeah, it's really fun to watch the cool rocket launches and see them landing on drone ships and all that kind of stuff. This, when I put this together 5 years ago, was brand new, and now they are actually successfully doing not manned flights, but the flights. Oh no, they did a manned flight to the space station with a reusable rocket, I think, like last year. The point of my story is, if you're designing an airport that's designed to last for 50 years, you seriously need to be considering this. This is going to be a thing. So this is why we don't take ridiculous ideas off the board, okay? You use them to create new and novel and more powerful ideas. I'm going to smash through a few other things just because it's fun for a little bit. Terrestrial transport, I think we covered this. We could walk. Hey, go back 100 years for me. Where before cars, or 200 years. I don't know. Like go back 300 or 400 years. If people had to move that far, they would have walked. That's out of all of human history, the most common way to move that far was 100% to walk. Nowadays, you could ride a push bike or a motorbike, or you could drive a car, or you could take a train. And remember where I said we're going to go broad and then back in, and then broad and then back in? So if we went broad, we got all of our ideas, then we come in on terrestrial transport. And then we went broad again, and we could walk, ride, drive, train. Cool. On train, let's go broad again. You can go conventional rail, high-speed rail, maglev trains, or we could dig a tunnel and go underground. So this is this whole divergent, convergent. Hopefully, the arc of this is getting smaller and smaller each time, but you can constantly go back and forth between the two options. We covered flight as well. We could go in planes and helicopters and drones. And as I mentioned before, you could take a glider. Longest unpowered glider flight. Taking bets. What do you reckon it is? So they power them. There's some amount of power that they put into them, either by a winch or another plane, and they launch them up into the air. It's the furthest somebody's gone. Just over 1,000 miles. Yeah, that's real far, right? 1,000 miles, like twice the distance to Melbourne. And it was a round trip, actually, so you could get to Melbourne and get back in unpowered flight in a glider. That is a possible thing to do. We could do some other dumb stuff. We could convey people on big conveyor belts. I don't know, whilst that's not super plausible, we definitely do it inside of airports. And remember, our problem was an overcrowded airport, so this actually could be a plausible solution to a slightly differently defined problem. I don't know, eventually maybe we'll be pneumatically conveying people. We could go by boat. Haven't considered it all yet, right? We could go by boat, we could take a cruise ship, we could take a container ship, we could go airboating, submarine, and what I want you to get out of this is there are different scenarios where even one particular type of transport, like water transport, can look really quite drastically different, and depending on whether you need to get in stealthily or you need to get in through marshland or what you're moving, can dictate better or worse solutions to the problem. But again, chuck them all up on the board. Okay, so I did kind of mention that doing this on a whiteboard is my preferred option, and that's definitely true. I think the best way to do this is to get a group of people in front of a whiteboard, and if you've got more people than can stand in front of a whiteboard, then they stand behind and they shout things, and you write them down on the whiteboard as you go, because I find the visual nature of this experience is useful. The fact that you have some sort of map that you are drawing lines between is much, much better than a list. Try not to write these down as a list. Try to scatter them out as a whiteboard, because you can draw all the arrows between things and it helps your brain to process it in multiple ways, which helps you to create more innovative ideas by joining together other ideas. And when you put them in a list, it's way harder to join those ideas together. Another really common way to do it is with post-it notes. So that's where everybody gets a post-it note and you can write on them and then you can go and stick them up. That is better when you've got a group of people who maybe are a little bit less hesitant to yell stuff out. This needs a really positive and engaging room to work well. This is a little bit safer, but I find it way less effective. Mainly because you don't hear the solutions from everybody else. If you're not going to sit and yell them out, then you're the only person who has that idea when you put your post-it note up. As I tried to cover, it's got to be high energy, it's got to be rapid. You cannot be slow with this. It doesn't work if you do it slowly. It only works if you do it quickly, because if you do it slowly, your brain will come up with reasons why this is a bad idea, and you don't want to give it time to do that. You got to smash it out really fast, and again, that can be difficult for some people, but it is a skill that you can learn, and you have to be willing to say something really dumb and be laughed at. That's fine. That's how this stuff works. We should be laughing. We should be throwing dumb stuff out. It's super effective if you do. This one thing that has to be addressed is no negativity. There's absolutely no reason for you ever to be negative in that room. And as soon as one person starts to be negative about it, you get them out of the room, because they will bring everybody else down. So it's nothing but positivity and it's nothing but encouragement. Okay. Really, really important. And no matter what, in the same thing as no negativity, don't take anything off the board. No matter how stupid, leave it there. Put it up in a corner if you need to put it up in a corner, but nothing comes off the board. Turn your ridiculous into reality. So you do all of that, high-paced, in a group, and then it's actually a really good idea to take that away and study it in depth. And you might want to then turn it into a list. You might want to cull it down. You might want to sit and really think about it for a really long time. And I'll often spend a couple of hours sitting there staring at the whiteboard, just trying to see solutions that everybody missed, to try and build a more complex, better solution. Because generally you're going to have to pull pieces from all over the board to assemble them to get a solution that's really, really good. And there might be many ways you can do that, and that can be a bit slower, and that's fine. So you do this big high energy thing to fill the board with stuff, and then you can go away personally and sit quietly and analyze it and study it and come up with something awesome. So that's my favorite way to do it. There are others, but that is my favorite and my most, the way that I would recommend you do it. You can also do it with a big piece of paper instead of a whiteboard. That's also super good. And if you're in a room, there's like a ES126 or whatever, you'll probably do it with a big piece of paper. That's also perfectly fine. Okay, so this is how I like to structure it. I jam my problem in the middle, and I make around the outside, I tend to put assumptions, constraints, and questions. And these will be a list of assumptions that we're making, constraints that we believe we have on the problem, and questions that we might have for our client. And whenever you come up with something that you don't know the answer to, or you're assuming and somebody else in your team isn't, you just chuck it down under these things. And generally, you'll then go back and relook at your scope and you'll use that to help inform these things. Or you'll go back to your client and say, hey, we need to know this, 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 and this before we can move on. So that's like the template I like to start with, and then we just scattergun stuff at it until we've got an awesome solution. The process, we've sort of been through this already, but I often find to help you structure this, throw up all the obvious solutions. Even if everybody knows plain is an obvious solution, you still write it down. Write it down, let's do that first. And then build off them. Take them, go embodiments or approaches or different ways of doing them, or mirror images or contrasts or something. Build from what you have. Throw your crazy things into there, and once your crazy things go up, go, why won't this work? And you go, why won't this work? Well, because the people will die if you put them in a V2 rocket, you idiot. Assumption, they have to survive the trip. Because nowhere have I said at any stage that anyone needs to survive the trip between Sydney and Melbourne. That is an assumption that you're making. It may be a valid assumption, but it may not be a valid assumption. Depending on your process, on your particular client and what you're trying to do, some of these things may or may not be valid. And okay, obvious example of people having to survive, maybe, but a lot of assumptions that people go into problems with are, oh, that's how we've always done it. Okay, so well, that may not be valid anymore. And we'll talk a little bit about that in the coming slides. So there's a couple coming slides where I go even more creative ideas, and we'll talk about that. Another really good thing to do is you make your list of assumptions and you start to run out of steam and you go, okay, these are all the ways that we can do it. And one of our assumptions is they need to survive the trip. For the purposes of this exercise, put a big red line through that. Let's assume they don't need to survive the trip. How does the problem change now? What becomes plausible? Because putting them in a rocket, you said will kill them. The rocket won't necessarily kill them. The landing might. But that doesn't mean space travel is not acceptable. It just means you need to figure out how to land a gigantic rocket on its end, which, hey, we've now done that. Oh, this is now plausible again, yeah? So, for the purposes of the exercise, put your assumptions up and then start drawing lines through them and going, what batshit crazy way can we solve this if we say gravity doesn't exist, or they don't have to survive the trip, or something like that? Because you might get some awesome ideas that you realize, I can actually make that work. Sometimes doing that process will help crystallize your objective. It gets everybody in the room on the same page. This is what we're talking about. This is the problem we're trying to solve. Sometimes it simply helps you to remember, oh, this was my list of assumptions and I've never written them down at any stage and shown them to the client. I should really do that. Helps teams get on the same page. I really like to do this process, and I like to start with questions and assumptions, because invariably, I've pretty much never done this in a team of people where we haven't argued about one of the assumptions, going, well, it's got to be this. No, it's got to be this. And argued about an assumption, meaning part of the team thought one thing and part of the team thought something else. And writing it on the board helps clarify that. And sometimes it does help you turn ridiculous ideas into reality. In fact, many times I've seen people do that. All right, and that's what I'm going to show you right now. So this is a slide from last year that I have not edited, what's about to come next, and I haven't edited in any way. So this was after, we did embodiments and approaches and all of that with terrestrial transport and things. Then there was this slide of chuck your creative ideas up. I don't know, maybe it'll help. It's like teleportation. Maybe we could get people between Sydney and Melbourne really quickly and really easily if we could crack how teleportation works. I don't know. Thinking with portals now, right? Once we're thinking with portals, things become much easier. What if we did it virtually? What if instead of physically moving people between Sydney and Melbourne, we did it virtually? I hope you're starting to see the irony here. We did it with augmented reality. Or, we did things through the internet. I normally use the example here of the Concorde, which used to be for flying people predominantly towards the end of its life. All it did was flew business people between New York and London, because business had to be completed face-to-face at the time, because that's the way the world worked. And then the internet became the thing, and then business didn't have to be done that way, and so the Concorde didn't need to exist anymore. So, the irony here is obviously plain. Oh yeah, sorry, I forgot about this. Trebuchets and stuff um, are perfectly valid solutions, and they allow us to come up with potentially practical ideas from our crazy ones. So that was a crazy slide in a pre-pandemic mindset. So not anymore. We're going to do things virtually. Okay, that's now a perfectly acceptable thing to do. That was a slightly different, well, a fairly drastically different set of constraints came to the problem, but we could no longer physically move people, so we started to move them virtually. Um, Lots of things pre-pandemic were considered impossible or at least too impractical to do. And that is so not the way of the world now. So there's heaps of things that we do in a particular way but that are based on a set of assumptions that are just totally not valid anymore. Um, I said I wanted to go to Melbourne because I wanted to watch a game of cricket at the MCG. If you went back 18 months and said people will pay to have a cardboard cutout of them in a sports field instead of going and all of this will be virtual, people would have laughed you out of the room, right? But this is now the reality that we live in. So going through this process allows you to explore these realities, throwing the ridiculous stuff up on the board that people would have in one stage laughed at, we turn into a reality. And we do this all the time. So I had to do exactly this last year. I had ENGG1500 12 months ago. It was a 100% online course. When semester started, we got to the first 4 weeks of semester, 100% face-to-face. In week 3 of semester, there was no talk of shutting the campus. By week 5, I was 100% online. So I had to figure out how I took my entirely practical course and put it online. And what I did was I got all of my tutors in a room and we went through the engineering process. It took us 4 hours, and in 7 days after that, I had a fully online course. It works. This process works, and it works by throwing up creative ideas and figuring out what is really important to us. Cool. This is an iterative process. So again, how I said, we'll often go divergent, convergent, divergent, convergent. You'll also go through this whole process potentially many, many, many times. So I had a job recently where I had to make a demonstration rig. Well, I didn't have to make it. It's still being designed, but we were designing a demonstration rig for some thermal storage. And we basically, as a team, had in our head more or less what it was going to look like. We'd gone through that really broad process and come back into, we're going to make some sort of box that will interface in roughly this way. We'd done one big loop of that. We did it again, and I did the same thing, put up questions, assumptions, constraints. And although we basically had our design in place, we still ended up filling 2 whiteboards with all sorts of questions for us to go back to our client. And that was one of the times we had some of these arguments about, is this an assumption that we are making, or is this the assumption that we are making? So you can do this at multiple levels. You can do it big and broad and creative, and then when you kind of get a solution, you can do it again in a far more practical way. And when you get a solution, you can get this all the way down to, I've got 2 things that I want to fix together at a 90-degree angle. Do I put a bolt in it, a screw in it, a nail in it? Do I glue it? What type of glue do I use? You can do the same process there. It's a much more contained version of the process, but it's valid at all stages. Cool. This is where we may want to come back to our scope. So hopefully you do this, you end up with this huge big list of assumptions, and you'll almost certainly end up with a huge big list of questions for your client. And you go back to your client and you relook at your scoping process and go, hey, this solution may work. Is there anything that we didn't think about in our scope that needs to be put in there? Or is this thing that's in our scope actually phrased the way we want it to be phrased? Because it excludes us from doing this, and I don't think that's really the purpose of the scope. So you can go back to them, go back to your scope and look at it. And hopefully make a better scope. Go back to your client, talk to them. Cool. So this whole process is iterative as well. We do creative thinking, we go back to our scope. Maybe we have to do creative thinking again after that because we have a better refined scope. I don't know. But don't feel like it's a one-shot thing. It is definitely an iterative process. Okay. So I think this is the last slide, or we've got one or two more slides on this section. So filling a board with 100 ideas isn't necessarily a useful exercise in and of itself. And I've been asked to do this in many, many different environments. Come up with 100 ideas on how to do this. Well, this seems like a total waste of time. I don't know. Here's a dumb idea and here's a dumb idea. Can we go back to real work now? It's not the purpose. The purpose of getting 100 ideas is to allow you to look at the problem from all aspects and see whether there's any part of it that you haven't thought of yet. And go, okay, my original idea is still what I'm going to do, but I'd not thought about, I don't know, landing yet. Okay, cool. Because of this really weird thing somebody threw out, I've realized I need to design that thing in a little bit more detail. Great. That means you've improved your design as a result of going through the process. And that may be all you do. It just makes you look at the problem from a whole bunch of different angles, and it makes sure you've got a perfectly well-rounded and brilliant solution that's not going to fall over at any stage. That could be great. Or you might take a few crazy ideas and stitch them together and come up with this new Frankenstein's monster version of something that is actually amazing from all these creative ideas. That could also be perfectly valid and perfectly good thing to get out of this. Or you will see something that nobody has ever seen before. There is, people get locked into ways of thinking. We talk about first choice fixation and stuff like that, right? We talk about assumptions. People get locked into a way of looking at the world. We can now look at a whole bunch of things that we do in life post-pandemic with a new viewpoint and go, actually, there are new ways to do this. There is new sets of assumptions, and you may be able to create things that nobody's been able to create before because you're looking at it through a slightly different lens. Okay? This is why we want to fill the whiteboard with ideas. If you do what you've always done, you'll get what you've always gotten. So if you jump to your first idea, I can guarantee you that 500 other people have already had that idea before you, and they're far more advanced than you are. If you can do something like this, you'll either hopefully get a more well-rounded or a more creative or a better solution than people who have come before you. Because odds are you're not the first. Cool. All right. So we've gone pretty divergent. We've got a whiteboard full of stuff. How do we pick which one we're actually going to use? How do we figure out which one the best one for solving our problem is? Now we apply the wet blanket. We're going to apply this in two ways. We're going to have two different things that allow us to narrow our solution space down and then evaluate plausible solutions. So the first one is narrowing our solution space down to what's plausible. This is where we come in with our scope and we apply yes or no questions. Does this thing fit within our scope? So you don't use your scope when you do your creative thinking. You ignore your scope for that process. Then you come in and you put your scope in and go, okay, our scope says we've got $5.3 billion. Inventing a teleporter is going to cost more than $5.3 billion. Teleporter is out. It's a yes or a no. It's nothing that's on a sliding scale. It's something you can answer with a yes or a no. I cannot build this for $5.3 billion. It's off the table. This would take more than 10 years to develop. Off the table. This can't move 10 million people a year. Off the table. Yes or no questions only. And you will find that this culls 90% of your solutions. If you did it properly, this should be a massive culling step. Generally, these are things that external factors set, so it comes out of your scope, and that's generally set by your client. Occasionally, it will be set by things like the laws of physics, which is fine. A lot of these things will be set by your assumptions. So remember we said it was an assumption that the people had to survive the trip. You can throw that out the window, but maybe when you do your creative design process, you throw it out the window, but maybe you put it back in when you come to this step, all right? So throw everything up on the board, but when you come to constraints, then you can start to cull. This is supposed to be one of the things, knowing this step is coming, is one of the things that gives you the freedom to be as creative as you want. Yeah, it can be outside of scope. Yes, it can be implausible. Throw it up on the board anyway, because this step is coming, and you're just going to put a big red marker through like 90% of your options. Great, that's fine. There's absolutely nothing wrong with that. So when you're doing the ideation step, the divergent thinking step, do it knowing this is coming. Don't premeditatively take anything off the board. Put everything up there and then come and do this, okay? So it's never okay to say, no, 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 that's outside of scope. I'm not putting it up. You put it up anyway, and then you just come in here and you draw a line through it later. But you just got to make sure you've got a valid yes or no reason why you put a line through it, and that you can convince your client of that. So they're constraints. Generally coming from your scope. Remember how I said your scope will help us later? Way back, like, what was that? About an hour ago? This is where it helps you massively. It helps you cull this list of things down to a plausible remaining set of solutions. So after that, every solution you've got left is a plausible way of solving it. It will work. And what that means is, depending on who your particular customer is, there's probably a better or a worse solution in this. They're all plausible. They all work. They just work better for some people than others. And then we need to go through that and figure out which one is best for us. So a lot of the time when I'll put something like this up, people will go, you just take the cheapest one. And while sometimes that is true, and if you've got very well-defined problems, like build me this building to hold one lecture theatre of this size, put out this as job scope, and you don't care about anything else, yeah, you take the cheapest one. But most of the time, that's actually not how it works with humans. I didn't buy the cheapest car that would get me from A to B. That was my scope, but when I saw the different options for cars, the one with the turbo and the powerful engine was going to be a lot more fun than the cheaper one that didn't have those things. And so I didn't buy the cheapest one. I evaluated a cost versus an enjoyment, and I picked something on the spectrum, right? So very rarely is cheapest best. Oh, my GIF isn't working. I'm going to try and get my GIF to work. Oh well. This is a GIF that you may have seen before, and it's just good, fast, and cheap. And as you select them, you can't select all three. You may have heard this before. You can't have something to be good, fast, and cheap, all right? You have a limited set of resources. If you invest more into one aspect, you will generally have to suffer in one or more other departments. Going, I'm going to be the best at everything generally just means you're equally okay at everything, or maybe you're equally bad at everything, but you won't specialize. This is not something where you can just be better than everything. The more you invest in one place, the less you will have to invest in others. And that resource might be money, but it also might be time, or it might be reliability, or it might be enjoyment. There's a whole bunch of things that it can be. Where people decide to put their optimums is generally based on their individual circumstances. So if we look at getting to Sydney and Melbourne by the Concorde or the cruise ship, the business person might want Concorde because they need it to be really fast, and they don't care about the cost. Whereas the retired person might be cruise ship. They've got all the time in the world. They don't care how long it takes, but they want it to be super comfortable. Yeah. So this is different humans with different personal considerations, finding different optimums, and you designing a solution that maximizes the ones that are important to you. So this I call performance criteria. Okay. Different to constraints. Constraints are yes or no. Performance criteria are on a range. They're on a spectrum. And they're almost always in competition with each other. So, we can look at this. When you are in college or university, your social life, your grades, and how much sleep you're getting, time is your resource here, right? You have a set amount of time, and you need to determine where in that triangle you want to sit. But as you move towards one extreme, you have to take away from the others. So this is essentially performance criteria. All right? They help us to answer what is best. Now, okay, this is a different example. I like this example. I totally ripped this from Top Gear, by the way. Let's just assume, for some reason, that we've been restricted to driving a car, and these are our only two options. Daihatsu and the Ascari A10. somehow these are our two remaining options. What's better? Well, let's put some criteria up on the board. They have a price. One's $11,000 and one's 350,000 pounds. Sorry. They have a fuel economy, which the Daihatsu is better at. They have a weight, and the Daihatsu is lighter. They have a top speed. The Ascari wins that one, and an acceleration, which the Ascari also wins. But the Daihatsu has more doors, more seats, more boot capacity, and more safety features. So, the Daihatsu wins in all but two categories, essentially, right? So it's the better car, yeah? If you had to drive to Melbourne, that would be the car you would take. Probably not. I'd prefer to drive the supercar to Melbourne. What happened? But it lost. It lost the competition of how many reasons is it good? Like 8-2. What's going on? Well, performance criteria need to be weighted, okay? So how do we assess which one of these things is better? We do write down what are all the things we want to assess it on, and then we weight those things, and then we score our different possible solutions against them. So I've got a table and a matrix that does that. But it's really important for us to understand that in order for us to evaluate between different solutions, we need to know what we want to score them on, and we need to know how important those rankings are to an individual. Understanding your problems, yep. Putting numbers to this is hard. So what I'm going to show you is a matrix that's full of numbers, and it's going to imply that these are hard numbers that I knew exactly. It's not true. You make them up. You do your absolute best to get an accurate number, but you make them up. And putting meaningful numbers to these things without really advanced models is really hard. Now, the better you've got models and assumptions down pat, the better you can put numbers to these things. But if you've got coarse models, you're not going to be able to put good numbers to them. And because you might still have hundreds of solutions at this stage, you do not have the time to make really advanced models and simulations of everything. So you're going to have to go with some pretty broad numbers. So it's really hard to put numbers to these things. And it means if you get anything that's within 50%, that's probably your error bar on these things. Okay. It's more important generally that you can communicate and explain why you use the numbers you use than the actual numbers themselves. Okay, you all have the same project brief. You will all do this step differently. And this is what will create teams on test day who have targeted different optimum solutions, is because they have either explicitly or implicitly assigned different weightings to different criteria. That will mean pretty much everybody else on test day will think your team is wrong, okay? And you will need to be able to defend the decisions that you make. And it won't be, oh, I ranked speed a 6 and comfort a 9. It'll be, I ranked comfort above speed for these reasons, okay? So being able to have that discussion will be super important. All right, so this is the decision matrix. I'm going to show you step by step how I built this and how I calculated that plane was the best solution. So what I did first was I wrote down, and again, bear with me, let's assume that these are a bunch of potential solutions that you came out of your design thinking process with. We could take a car, a plane, we could walk, take a boat, go through space, or a train, okay? And then what you need to put in are what criteria you're going to assess them on. So you should probably have more criteria than this, but for the purposes of the discussion, we've got cost, time, comfort, and planning. Now you'll see that for, say, cost, for example, it's 1 divided by cost, so it's the inverse of cost. Basically, it just means cheaper is better, not more expensive is better. So 1 divided by how much it costs is better. Bigger numbers are better in this. It's just the way that these things are done. All right. And then what I do is I rank those, or I weight those criteria. So there's a bunch of different ways you can do this. The way that I did it here was I just went cost, I'm going to call a 1. But because the actual magnitude of these is arbitrary. So I'm just going to call cost 1. And I'm going to say time I think is more important than cost. So it's getting a 1.5. I think comfort is less important than cost. It's getting a 0.6. And I think planning is less important again. It's getting a 0.3. So what I did next was I ranked each of the options against each of the criteria. So I went down cost first, and I made the most expensive one a 10, and I just tried to comparatively rank all of them from that point. So plane got a 10, and then I just went car's a little bit more expensive, so it gets an 8. Something like spaceflight is uber expensive, so it gets the lowest number I can put in there. And then I did the same for timing, planning, comfort. And then all you need to do is work across each row, go what did your criteria get, multiplied by what was its weighting, and give it a total. And the one with the highest number wins in this scenario, okay? And this is a numerical way of collecting all of that data together and using it. And it's a kind of broken system, all right? It's not a super accurate way. I would say plane versus car there, 31 versus 24, is totally within the error margin. You could very easily tweak a couple of these numbers by a tiny little bit and very easily get plane above car. All that this tells me is walks out, boats out, and plane and car, maybe train or spaceflight, are usable options. And I've seen things done at lower fidelity than this, so lower accuracy than this, and been used to plan projects costing between $10 and $100 million. I was a little bit scared when I saw it, but I have sat in rooms where we have done exactly this. So let's talk about some of the flaws with this way of doing things. Not necessarily flaws, but some things that you need to be aware of. Insufficiently detailed designs. So if I say I'm going to take a plane, am I talking about just the plane flight? Am I considering in this calculation that I have to first drive to the airport and then the plane takes me to another airport and I possibly have to drive to my actual destination? There's more complexity to these things than you can probably think about at this stage. So this can be a flawed system because of insufficiently detailed designs. You don't know enough about the process yet to really evaluate it. We also might be missing some criteria. So I've only got 4 things up there that I'm rating this on, but there's probably loads of other reasons. A lot of people have, environmental reasons would dictate which of the options they would take. Other things like if I drive, I then have a car, and that could be super useful to me in the middle of Melbourne. It could also be awful because I might have to find somewhere to park it. So this is missed criteria that I don't particularly have. Also, how did spaceflight come in at like 3rd in our list? Spaceflight is a ridiculous option. How did it do so well? Well, the reason it did so well is there's bounds on my scoring system. I can't give something a score below basically 0. And as a result, it artificially inflated how well spaceflight should have done. Basically, you need to use your brain when you look at these things and go, yeah, okay, whatever. The algorithm said this, but that's because of some one ridiculous outlier that's in here that really shouldn't be considered, okay? And also, really importantly, personal bias. Let's have a look. Look at Boat. Boat did terribly, right? Cost, time, comfort. That's the one I'm looking for. 0.1 out of 10 for comfort. Why did I score Boat so ridiculously low on comfort? Cruise ships are normally considered very comfortable. Yeah, Dylan gets seasick. That's why Dylan thinks boats are awful. But you may not get seasick. You may think boats are super comfortable. And you may give that a really drastically different number. So personal biases are generally seen super obviously in these types of things. So you'll notice when people want to put biases in, sometimes they will bias the number and they'll make them bigger or smaller, but sometimes they'll either double up criteria or deliberately omit criteria in which their favorite solution does better or worse. Now, if I'm going to sit here and say this has got all these flaws in it, why do I recommend you do it? Well, I actually recommend people do this not necessarily just to make a decision, whilst it can be useful for making a decision. it's a really good thing for a team to go through, because a team sits there and goes, I got totally different numbers for you. I gave a boat 10 out of 10 for comfort. How did you give it 0.1? Well, I get seasick. We're making decisions based on either false assumptions or personal biases where we don't agree. So if you do something like this in your team, which I would 100% recommend you do it as individuals and then bring it together and look at it. And what you're looking for is, where are the differences? Where did somebody give this an 8 and somebody else give it a 2? Because that's the important thing. Don't average them. Do not just take them all together and average them. That is not a useful process. What you need to do here is go, where are our biggest discrepancies and why? Get your whole team on the same page. That is what these things are unbelievably useful for. Okay? Cool. Couple more things. All right, so the things that I had up here so far are kind of hard criteria. They're criteria, at least for things like cost and time. I can put numbers to these, right? I can say it takes X hours to get there. This other solution takes Y hours. Y is 2.5 times X. They're things I can put numbers to. People are biased to using more numerically measurable criteria in those types of charts. Things that they can deliberately put a ruler on or whatever and measure. That doesn't mean the soft or the immeasurable criteria are less important. It just means they're harder to deal with. So comfort, for example, is probably a more difficult parameter to capture. That doesn't necessarily mean it's any less important, right? This is super relevant. Some of the soft criteria that can be super important is risk. Is this a risky or a very safe way of doing things? That is going to drastically determine which are better or worse solutions. Environmental, cultural, social, and aesthetic are also really important. As I've said before, things like environmental decisions are massive drivers in decision making nowadays for most people, often well above things like cost. People will very happily pick an environmentally friendly option even if it costs more. It can be very, very difficult to put a number on environmental impact, but that doesn't mean it's not important. Okay? Cool. A lot of the reasons why people will pick an operating system, for whichever one you prefer, but why people pick particular operating systems is very rarely due to hard criteria, maybe Linux users. But if you're picking between Macs and Windows, you're generally picking it because you like the way it feels, or you like the way it looks, or something like that. And it's huge business based on aesthetics, or based on culture, based on social interactions, can massively determine which are better or worse engineering decisions to make. Cool. All right, I'm going to go down really quickly, a little bit of an aside here. This is something that I have a bit of an interest in that I think is super cool. If you don't get this or don't like this, don't worry, bear with me through this slide and then just ignore that it ever happened. There's this YouTuber called Spirit of the Law who makes Age of Empires 2, which is a computer game, YouTube videos. And he does this really, really cool thing where he goes through, and in Age of Empires, it's a game where you play as like a medieval race and you build up an army and a town to give you money to build more army, and then you go and try and destroy another person's town and kill all their peoples. There's all different nations or races you can play as, or civilizations you can play as, like you can play as the Romans or the Franks or Mesoamerican civilizations or whatever, and they all have different strengths and weaknesses. Depending on those strengths and weaknesses, certain strategies like building archers or knights become better or worse. What this guy does is he goes through each one of those civilizations and he ranks them according to a whole bunch of things like their economy, how good they can make archers, how good their stables are, all that type of stuff. And when he did all of the different civilizations, he then made a video where he put all of them together and he ranked them all. This is a performance criteria matrix. This is a decision matrix. And he goes through and he puts all of these numbers in, And then he spends a whole heap of time going through his process and talking about where it is flawed and where it is good. And he talks about things like convoluted criteria and poorly weighted criteria and personal bias. And it's just this amazing analysis of his own decision-making process. And I'm pretty sure he has a maths degree or an engineering degree. And like, this is exactly what we are talking about. So if you're interested, I'll put a link in the description below. When I saw it, it just like blew my mind about how amazingly cool it was. If you're interested, please go and watch it. If you're not, feel free to totally ignore it. Cool. All right, so to wrap up, constraints and performance criteria. We have constraints, which allow us to take 100 solutions and cull them with yes or no questions into a batch of plausible solutions. Performance criteria allow us to evaluate those solutions based on how well they will perform for different individuals, and based on how well we understand the problem, we pick which individuals we want to optimize for. So they allow you to these things are what allow you to make decisions and then to defend those decisions when somebody criticizes you for them. They need to be specific. So if you write down cost, that could refer to the capital cost of building an airport, or it could refer to the cost of a flight to go from one to the other. You need to be specific about which one you were talking about. And you can have it twice. You can have capital cost, user cost. You need to be careful that you don't overlap things. Does a car need to be powerful, light, and fast? Well, generally no. If it's powerful and it's light, it will, by physics, be fast, because that's how that works. You also need to make sure you cover everything so you don't miss anything, like environmental factors. Even though they are hard to put a number to, they are very important. And if you're left with some ridiculous ideas, it's probably because you're missing something in one of your performance criteria. Now, this is the super useful thing to always remember, is something can be both a constraint and a performance criteria. And cost is a big one. Cost. It cannot cost more than this. I don't want to hear about any solution that costs more than $5.3 billion. Great. It's a constraint, right? Because it's a yes or a no question. But cheaper is also better. So it's also a performance criteria. Most of your projects have a maximum cost of $100. If it costs more than $100, I don't even want to hear about it. It's an unacceptable solution. But also, cheaper is probably better in most of your designs. So don't think you can spend $99.99 just because it's a constraint. It should also be a performance criteria. Cool. So let's assume you've gotten through all of this, you've done everything I said, and you've still got 3 or 4 solutions that are doing pretty well on your performance criteria. Maybe there's 30 or 40% difference in the range up the top, which is your error bar, and you go, none of this is enough to wipe any of these out. What do we do? Well, there's a bunch of things you can do from here. You can go back to your client and pitch these 3 or 4 things to them, and they might go, yeah, okay, I like that one, do that one. Or, hey, here's some more parameters that might help you decide. So feel free to go back to your client with 3 or 4 options, not just one, and have that conversation with them. I do it all the time. It's great. You can go and do more research, and hopefully that allows you to put better numbers into your performance criteria decision matrix, which allows you to separate these things out a little bit more. Make better models, again, same reason. Or you can start to make prototypes. So you can take your 3, 4, 5 different solutions and you can start to build them. Maybe not all of them, but find the critical components and start to build them. You might start with 3 or 4 different builds and just keep pushing them until one of them hits a critical failure and you go, okay, this is awful, I'm not doing that, I'm dropping it out. And maybe you've got 2, and then maybe you hit another critical failure and you drop it out, and then you've got a final solution at the end. But you can start to build. And we're going to talk about prototyping next week, okay? To give you some perspective, a project that I'm currently involved in at the moment has an 18-month development. So we're going to do this for 18 months before we settle on something that we're going to move forward with. You're not. You've got 12 weeks to finish your project, but you might spend 3 or 4 of those weeks carrying a couple of ideas through. Once you do all of this, go back to your scope, go back to your problem definition, and see whether you think it's all still valid. Does the solutions that we have really fit that initial problem that we identified, or have we gone down a bit of a rabbit hole and got a bit distracted? And is there anything in your scope that is limiting you here? Because sometimes you'll look at your scope and go, well, with $5.4 billion, I could come up with this absolutely amazing solution. Give me another 100 million. And they might go, yeah, cool, that's rounding. Go for it. Give me something way better. How much are these dead hard lines? What can you talk to your client about? And if we do all of that, hopefully we can finally answer the question, what is the best solution to our problem? It's not just going to be a solution that works. There are many solutions that work. It's going to be the best solution. Okay? And we got to here by going through a systematic method to solve our problem. That's how we know that we are right. And it may be your first idea. Maybe the absolute first thing that you come up with, and you go through this whole process and you land exactly where you started. And you know, what the hell was the point of that? Well, now you know. Now you know when somebody throws an idea at left field, from left field at you on test day, you can go, yeah, I thought of that. And this is why I didn't adopt it. And when I sit there in investor meetings, they will fire stuff at you. Why aren't you doing this instead? We did. We checked it. This is our reasoning for why we're not doing it. And if you don't have that as a solid set of answers, if you just went, nah, my idea is better, you're not going to last very long, okay? Because you don't know that it's best. But if you do this process, you will. So that's our engineering method, or at least the first half of it. From here, generally what we do is we go into a detailed design and construction phase. So we start to do specific number design, we build things, we give them to clients, we evaluate the process, and we generally do that as a loop. That's what you're going to do in the back end of your projects. You'll also often see it drawn up like this. So that's the more detailed version. That's once you know what you want to build, then you can enter this phase. And again, we're going to talk about prototyping next week. Now, just before I leave you, and we're like 3 slides to go here, there are some issues with this methodology. As I've alluded to, you can put personal bias into this process to make whatever solution you want fall out and look good. You just neglect to put in certain constraints. You just up some weightings on some performance criteria, and you can make anything work. So if you've settled on a solution and you just want to go through the process, you can definitely make your solution come out to be the best. You're wasting everybody's time, but sure, you can do that. This method doesn't prevent a bad actor. Somebody who wants to be malicious can certainly be malicious in this process. It's not for that. You should, however, be aware of it and try and work on removing your own personal bias. Some people will say that it takes too long to do for small projects, and it's too big and it's too complex. And you'll get some pushback from here going, why are you wasting time with this? You can go through this entire process in 15 minutes flat, and I have done it before in that much time. It just depends on how big your problem is and how many times you want to go out and in and how broad you want to go. But you can do it in 15 minutes flat, or you can do it over 18 months. You can scale this, but yes, you can get caught in it and it can be a waste of time. Don't get caught in it. And not all the steps make sense in every application. And that's totally valid. The steps that I went through here, you're not necessarily going to go through them the same way when you're trying to build face shields in the middle of COVID versus put an engineering course online. It's going to be different. So you don't follow this rigorously. If you try and follow an engineering method rigorously, yeah, I agree with you. It's a waste of time in most applications. You got to be flexible. Cool. So from here, where are we going now? You can start to think about your problem and you can start to do some problem identification now. Don't try to solve it yet. Again, week 5, you're going to do your divergent thinking brainstorming session, but start thinking about your problem now. Most importantly, smash your workshops, all right? That is the most useful thing you can do without a shadow of a doubt, is show up to your workshops and smash your way through that content. Really, really study it, really, really learn it. That's going to make life so much easier for you. Your videos this week, links in the description below. As I make them, it's going to take me 24 to 48 hours to finish them, will all be about human-centered design. So engage with them, watch them, hopefully learn, try and empathize with a user. And you will have an assessment to start. I'm going to chuck a video up. Link will be in the description, but I'll also spam it, email it to you, and all of that kind of jazz, which you can sort of start this week. Do you start this assessment by smashing your workshops. It's write a report on the stuff that you've learnt in your workshops. So you do the assessment by doing the workshop. So the number one thing to take out of this, absolutely smash your workshops for me. Everything will be awesome. And with that, thank you very much. We are done.